Hi everybody, I'm Dr. Claudio Paganini and I'm a mathematical physicist working as a postdoctoral research fellow at the math department at Monash University. My research focuses on the reason why you hit the ground when you trip, i.e. I'm interested in gravitation and everything related to it. So basically my main focus are black holes and the universe. Today, in my interview with Adam, I will try to explain to you the concepts underlying a new approach for a theory of everything. And this theory might be able to explain why matter, and thus why we exist in the first place. So, what I want to explain to you right now is the importance of the ground state in quantum mechanics. Now, in classical mechanics, if I have this ball and I place it on my hand, it can basically sit there forever and nothing happens. And it doesn't make a difference whether it sits on my hand or whether it sits on the ground. Now, if we go to quantum mechanics, essentially what happens is that everything is shaking. You can basically think of that. So like it's shaking, and eventually, if the ball is in my hand, it will fall down. Now, the thing is, if the ball is on the ground and we shake all of the planet, nothing further will happen. So this is essentially the ground state and the importance of the ground state in quantum mechanics. From the ground state, no matter what happens, the particle cannot, the quantum system cannot decay any further. So if I drop the ball here, it will never hit the sand because the sea level, in a sense, prevents it from falling any further down. And now, essentially, you have the sea level of the Dirac sea takes over the role of the ground state of the system. So instead of having a ground state where it can't decay further, it is now you have the Dirac sea where all the states are filled to that certain level. Okay, now when Dirac tried to describe the electron, the equation he derived had essentially no ground state. So you can imagine that as almost like an infinite staircase. So if a quantum mechanical system were there, it could decay forever and release more and more energy into the environment. This is of course unstable, and what Dirac did, as the good physicist is, he was like, well, it's not a bug, it's a feature. And he basically took a certain step, labeled it step 0, and then he said, well, the staircase is flooded to this point with water. So now, when you have a quantum mechanical system there, it can decay and eventually it falls down and it never hits the ground because it can't cross below the Dirac sea level. So this staircase filled until the 0th step is what is now referred to as the Dirac sea. So as a consequence of this ad hoc fix, Dirac figured out, well, what happens if I remove some water below the staircase, like below the sea level? And that is essentially how he came up with the prediction of antimatter. So if a particle above the sea level behaves like an electron, then if I remove water, or like if I remove a state below the Dirac sea level, so if I have a state that is not filled, then it will behave equal and opposite to the state that is above the sea level. Now we can see this we can gain an intuition for how that works using the water droplets here. So when I use the two syringes, you see one is filled with water in the air and one is filled with air in the water, and when I empty them, the two move in the opposite direction. So the water bubbles, the water droplets in the air move downwards, while the air bubbles in the water move upwards. So now I will try to explain to you a couple concept or the conceptual basis of the causal fermion system and how physical reality has to be seen or can be interpreted within this framework. Suppose you're in a little boat on the ocean. The water beneath you is made up of various currents, lots of small particles, various movements, but all you really care about, anything that you can feel while in the boat, is just determined by the surface of the ocean. In a similar thing happens with the Dirac sea in the causal fermion system framework. So all we see as physical reality, according to that framework, is deformations to the Dirac sea. So you can think about when you're in the little boat on a flat ocean, as at the moment, it allows you to travel across, but nothing much happens. That's essentially what vacuum looks like and flat space. Now, if you have small deformations or smooth waves, you might feel a little something when you're in your boat, and that's essentially what the fields like electromagnetism or the curvature of space-time would feel like to you. So you feel a little something. Now, the final thing is when you have a real rugged sea, like when it's like splashing and you have like bubbles and rolls and everything, and you can't really separate the surface so clearly anymore. And that is essentially what then the world would, in a sense, look like when you have matter, and so when you have particles and antiparticles and everything flying around. So this is essentially one way that you can interpret the physical reality in the context of the causal fermion system. Now, this framework is still very much under development, so everything that I tell you here is very much in development. So it's not settled, we don't have any experimental evidence for it or any like precise predictions, but we are currently working on an idea how this framework could describe why matter exists in the universe to begin with. Now, obviously, so when you look at the Dirac sea, matter and antimatter are in perfect symmetry. So when you remove a little droplet of water, then so when you remove one state below and you put it up, you always get a pair. You always get a particle and the antiparticle together. But obviously, at some point in the universe, this symmetry must have been broken because, well, we are here, right? So there is more matter than antimatter in the universe. And how that came to be is what we're currently trying to answer. According to all current theories, particles and antiparticles are mirror images of each other. So whenever you create a particle out of vacuum, you get simultaneously an antiparticle. So there's a perfect symmetry there, as you can see, between the buildings and their reflection in the water. Now, the thing is, when we actually look in the universe, then there is obviously more matter there than antimatter because, well, we exist, right? Now, so the thing is, the symmetry has to be broken at some point. So there should be some buildings that have no reflection. Now, how this can happen is what we're currently trying to understand in the context of the causal fermion system framework. So in this little video, I tried to explain to you the concepts underlying the physical reality in the causal fermion systems framework. Now, to be clear, this was my current best understanding of the framework, and other people working on it might not quite agree with this interpretation. So take it with a grain of salt, and maybe there will be an update soon when we understand better what's actually going on.